In this video, I'm going to talk about double integration. So double integration is a nature extension of the standard integration we talk about. So basically, if I give you integration, let's see, ft over this t from a to b, and if I draw it out, let's see here, this is from a to b. Okay, my x-axis is t, and this blue line represents what ft looks like from a to b. So you can sort of see by the definition of the integration, what the integration is trying to do is trying to figure out the area of this shaded area, the size of this area of this area. That's what is the integration trying to do. Okay, we also talk about in the previous several lectures, we talk about the line integral. Okay, we talk about line integral. There are two types of line integral. Okay, one is this type of line integral. We're actually not talking about integration over a to b along the x-axis. We're talking about if you give a line, okay, is a line which is a curved line. Okay, it's a curved line. So I'm going to integrate some function fxy. Here is not fx anymore because we have this is a line. It's not on the x-axis only. So for every point defined on the line, and I have a function fxy defined as a magnitude associated with a point. You sort of can see if this is a flat surface, okay, region, you calculate the size. This one is a curved surface, okay. At every point, we define a height associated, which is fxy associated with that point. And as you move for xy along the curve defined by this s, for example, then you can compute. What the goal is trying to compute is the size of the curved surface. It's not the flat surface over here. So that's the difference. So we also have the integration of this is called line integral over a scalar field. Now we have line integral over a vector field. We basically have a vector field defined by v xy, okay, which is vector. We have a trajectory which is defined by s, a line, which is xt, yt, and let's say for 2D space only. And let t move from t0 to tf, so we can define a line. And the line, the goal is trying to figure out, hey, what is the work done if I move from the beginning to the end across along the field. Okay, this is called line integral over a vector field. So what we do is we actually try to compute the dot product of v dot dr. Okay, and what we do is we just to replace everything, all xy, by its parametric form, which is given by xt y sub t. So we replace every x by xt is a function of t, and y is a function of yt. If you have dimension, you have z by zt. Anyway, it's just a function of t. So you convert it back to the standard integration, and you can do the dot product, and you can do the integration. And similarly, even for the line integral, you can see is you convert it back to the standard integral. So we all back to this form. Okay, even if we have line integral, it actually come back to the form we know how to solve. Okay. Now next we'll talk about a double integration. Double integration is different from the single integration. Is we don't have this form anymore. It's more complex than this one. Okay. All right. So let's first give you a motivation example. What is the double integration trying to do? Okay, and how it is different from the integration we talked about before. You were very familiar with is a single integration. Basically, we'll call it single integration. So double integration has notation wise as two integration signs, integral, and it has a function of fxy, and over d sigma. So sigma is the integrated sigma over this s. S is an area. So difference here is, if you look at this one, now this one you over a to b, you integrate over a line, or you over this line, either a straight line or curved line. Okay. Now what difference is, hey, we're integrated over area. Okay, so this means that, hey, for a little tiny bit area, I'm trying to integrate that one over some function defined for this little tiny area. Basically, say I have a little tiny area over here, or I have a function fxy defined for this tiny area, assuming that this doesn't change too much, of course. Then something defined for this little pieces. For example, you can consider this as, hey, if it's raining right now, I have a density over here for this little piece area. I'm trying to see how much water I can collect for this little piece area. Okay, so that's why you integrate over an area instead of a line. So that's the fundamental difference between the standard integration we know and the double integration. Okay, we can even have more like triple integration, that the little cell, or only a little piece is almost straight line. That's for single integration. That's the main differences. Okay, so you can sort of consider, hey, I'm trying to do, if you consider for the single integration, what you're trying to do is you break this A to B, this line, into very tiny infinitesimal area and try to figure out how for this infinitesimal area, so what is the integration looks like, and you put all of them together, you do the integration, you do the sum. Okay, the similar way is, hey, it's the same as something like I'm doing the sum across all the tiny cells of xy, fxy over d sigma. D sigma is the small cells. You can divide it into tiny cells, many tiny cells. For each cell, you compute this, then you compute the sum. So that's the physical meaning of the double integration. Okay, so essentially what it's trying to do is, I would mention to you here that the ultimate goal of the double integration is try to write it still the way as a single integration, but we have two kind of steps. Basically, you can sort of see eventually when you try to compute a double integration, what you do is, hey, let's first do an inner loop of sort of integration. It's a single integration only over, for example, dx. Now here you consider the y to be constant when you integrate over dx. Then you get a function y, then you integrate over y. So that's what happens when you try to compute that double integration. Okay. All right. So now I think it's good to give a little bit more example and see the key challenges. Okay, and how we solve the key challenge. Okay. Let's say right now, like I mentioned before. Okay, let's say I want to compute, for example, the water collected for this some area. Okay, let's say the squared area starting from A to B, and this length along x-axis is from A to B, is B minus A basically, and for y is from C to D basically. Okay, so that's the area, and assuming that my density fxy for every point that I collect for the water, that water density at each particular point is given by fxy. Okay, so I want to see how much water I can collect for the entire surface. Okay, so the key idea that we write this one in this way, the key challenge is, oh wait, how do I write this one into this form, like the inner integration and outer integration? Before we do that, we want to see what does this mean for the inner one. Okay, so for example, okay, I'm gonna write this one. I want to figure out the lower bound, upper bound basically, right? So what does it mean? So when we integrate over inner one, okay, so for the outer one, we don't do change y anyway. So this y is constant. The reason because the outside is trying to say, hey, I'm going to swipe through all the possible y. So for the inner integral, it's what it's trying to do. Hey, let's say for a fixed y, I'm trying to figure out all the x. It's sort of like this. Okay, if I'm going to make y to be a constant, okay, which means, hey, y is going to be here somewhere, some value. Okay, I'm going to swipe through for all the possible x. Okay, this is the kind of slice. If you can see the slice, I'm gonna say, hey, how much water I can collect for this little bit of slice, kind of little bread. Okay, I'm gonna see how much water I collect over here. Then I can swipe through all the possible y. Okay, for this point y, I'm gonna figure out, hey, how much water I collect over here. This one I'm gonna collect over here. This point I'm gonna collect over here, and so on and so forth. You can collect. So if we swipe through all the possible y, you basically have all the possible slices, and all the slices stack them together. If you can calculate the water for each slices, yeah, if you stack them together, you can find all the water for this surface. That's what it means. Okay, that's the main idea how to write this one in the inner loop and the outer loop. So what the inner loop here is trying to do is, hey, I'm going to calculate the slice, how much water I collect for each slice, for the slice. This is for the inner one, is water collected for each slice. Okay, so the outer loop is trying to collect the water collected for all slices. That's what it's trying to do. So you can sort of think of the difference between the inner loop and outer loop. In order to figure out the lower bound and upper bound, just figure out, okay, for a y, for a random y somewhere, so what is lower bound and upper bound? This one may depending on the lower bound and upper bound for your region of y, because the slice, the very left of the slice and the very right of the slice depends on where you are, may depending on where what is the actual value of y could be. Of course, here it doesn't matter. It doesn't matter which y you have. You always start from A to B. So y here, for this example, F do here is fxy dx dy. So it doesn't matter what y you do. You always start from A and A to B. Okay, that's it. Okay. Now I'm gonna say, hey, what is the range for y? Yeah, of course, y is from C to D. So in other words, you first do integration of this. This is for each slice. How much water you will collect for a specific y, and outside one, try to calculate all the water you collect for the entire area. Okay. So that's what you do is once you figure this one, yeah, you can do internal one. The internal one is you consider your y to be constant, and then you do just the standard integration, right? Then after that, you get a function y, then you integrate over y again using the standard single integration, then you can compute the result. Okay, so I hope the concept will be not very difficult to understand. Okay, now let's give some examples to see how actually compute this double integral. Okay, all right. As I mentioned to you, to find the lower bound and upper bound is very important. You know, because after you figure out all the values, the computation shouldn't be very difficult. As long as you consider internal integral as you consider y to be constant, you do dx, okay? And all you can do then for the external one, you consider you just integrate over y. The other one I mentioned over here is you can also swap the order. Okay, you can also say, hey, I'm going to integrate of f x y dy dx. You can also, of course, use d integral over dy first and then dx. Okay, this one you consider the first one because you use integrate here is y, right? So basically it's x. So you know here consider x to be a constant, which means here consider x to be constant. You just do the slice along this way. You do all slices along this way instead of what I do for the y. Okay, yeah, that's pretty much the same. Like for each y, you do the slice, right? You try to figure out, hey, what is the integration, and what is the, for this slice, what is the smallest value you have for y? Is right? Yeah, of course, this is C and D, because for any x, your slice will be from C to D, right? So this C to D, and the external one will be from A to B, okay? Which will be the same. You can also do this way. Then you have inner one and you have outer one, which will be the same, okay? All right, so let's take a look at example that we have. That I can show you what do we do. Let's do one example. Okay. Okay, so example first one is calculate the volume of the cube. Okay, this is a pretty simple example. Let's say I have a cube which is so along x-axis the length is 3 from 0 to 3. Along the y it is 0 to 4. Along z it is 0 to 2. Okay. In order to compute the volume, yeah, of course I can do is consider this is for every point I consider from the x, o, y domain. This is the surface, the 2D surface I have, 2D area I have. And of course, for each one you have a height of 2, which means if I were to divide this one into little cube, little cube, I have a very tiny area over here. Hope I can draw it here. You have little tiny one over here, and the length, the height will be always 2. So you have little dx and little dy, and then you have the height is 2. So that's why this one, to compute the volume, you can write this one as integration of 2, which is the height, is always 2, right? Z is always 2, over d sigma, and over d is area. Area is S, entire area. Area is defined by x. S is defined by x from 0 to 3, y from 0 to 4. So that's my area. Because for every little cube over here, little area over here, you try to compute the corresponding cube, right? Little cube, and you put them together. Okay. All right. So this, if I look at the draw over here, make it just x, o, y, plain like a little bit easier to see x, 0, y. So x is from 0 to 3. Okay. 0 to 3. Okay, so it's here. and y from 0 to 4. So it is this area. Okay, this is the area that I'm talking about that you integrate over, okay? So in order to integrate, like I mentioned, you have to do the slices. How do we do the slices? You can integrate from x first. You consider y to be a constant. Okay, if I consider y to be a constant over here, okay, I have a slice over here. Okay, any y, of course. You do slice here, all those slices. So you want to take for the slice, each slice, what is the lower bound, upper bound for x? Yeah, for every y, it doesn't matter where you guess what the y value you have. The slice, to define the slice, that in this area, of course, you always start from 0 at any of the 3, right? Because it's always right from 0 to 3. So here you have 0 and 3. Of course, for y, once you do for each slices, how do we swipe all this area by using the slice? Yeah, because you have to slice through 0 to 4. So this is 0 to 4. Okay, so that's why I have lower bound for x 0 to 3 and lower bound upper bound for y 0 and 4. So once we figure out, we just have this, okay, right over here, and inner integration, and then we do out integration. Okay, that's pretty straightforward, right? For inner one, you do integration from 0 to 3 of 2 over dx, which is 2x, the integration of 2 over x is 2x, and evaluate the 0 to 3, so this guy will give us 6, right? And then integrate again of this one over y from 0 to 4, now finally it's 6y. 11 evaluated 4 to 0, so it gives us 24. Of course, this area you can see the volume, this one is just be given by 2 times 3 times 4. As we know, you don't even have to do the integration, it's 24. Which we just show that it matches the way we calculate using the double integration. Okay? So now I'm going to give it a little bit more complicated example. Okay, so this one is a little bit different. It's just the half of the previous one. The previous one we have a square. Now we have the half of that, the cube, right? Now we have half of that. It's like a triangle, the cheese, right? So if you cut a cheese, you have a triangle one, okay? The same way, still trying to integrate fxy of 2. You're still trying to figure out the volume of this triangle-shaped cheese type of thing. It's just half the previous one. You know that the size, the volume should be 12 according to previous one because only half of it, right? So, but if you want to understand how we do the double integration, it's important for us to figure out how to figure the lower bound and upper bound for integration. Okay, if we look again, okay, right up here, cut over here. So here, what difference I have is this is the area I have to integrate over, and for each little cubes, for example, the height is 2. It's still 2, right? So we can, for x, y, it's still 2, right? But the area becomes this. You know, it's not the rectangle anymore. It's just a triangle one. Okay. So if you look at it, if I draw it over here to see this, so if I have x, y over here, so x is starting from 0 to 4. So 0 to 4. Okay. Sorry, I make it a little bit confused. So make it a little bit straightforward. So y is also 0 from 4. Okay. So it's not. It won't be 12 here because the size for y is also 4. Okay. So for the previous one is 3. Y is 4, but x is 3. So now here x also moved to 4. So make it a little bit simple in terms of understanding. Okay. All right. So if I'm only talking about this area, okay, I'm going to really also this. So this for fxy is just 2. Okay, so we already know that. Okay, now I'm going to do slices. So the way now I'm doing slices will be different from the previous one. Assuming that I'm still want to integrate over x first for the internal one. Okay, and then I'm going to integrate the y. Okay, which means I still keep y to be constant. Let's do y to be a constant. Let's say y to be a constant. Okay, I want to cut it slow. Okay. Oh, so this is my slice over here. Okay. If I have another y, oh, I have a slice over here. If another y, I'm going to slice over here. And for y here, you have a slice over here. And another y over here. As you can see, for different y, the slice is different. Okay? Which means you don't start from the same point or any at the same point for different y. So as a matter of fact, the point, the slice, any of the slice always 4, as you can see right here. So you can say, hey, for the internal one, integration, the upper bound is always 4. Because it doesn't matter which y you have, it's always you end at 4, right? However, the starting will not be constant. For example, at this point, you start from 0. At this point, it grow until you grow 2. At this point, you almost starting with 4, basically, right? So we want to say the lower bound. I cannot have x over here because I want to integrate over x. But I can have y over here because, oh yeah, for different y, you have different value. Apparently, this lower bound value over here is a function y, okay? Because this is 4 and 4, right? This is 4, this is 4. So this straight line means at this line over here, this is a line which x equal to y, right? The straight line. Because this is 4 and 4, this is 0 and 0. So this line means x equal to y. So which means that, hey, if I'm y over here, because this starting point is on line, so this one is, if it's x, yeah, because it's equal to y. So which means, oh, for this specific starting point, the starting point depends on y value. If your value y is higher, this is 4, it's starting from 4. If the value is y is 0, it's starting from 0. That's exactly what happened here. Is the lower bound of here is y. The reason is y because the x value, the starting point of x, integrate over x, is for the slice. The starting point of x is equal to y. Means the starting point right here, starting point of x for each slice is exactly y. That's why I have y over here. Okay, after that, for the slice, if you define all the slices, how do I define the y? Of course, you have to let your y move slices from 0 all over to 4. Okay, because you have to move all over to 4. So this is from 0 to 4. Of course, as you go up, your slice becomes smaller, but you still have to swipe all the possible y, which means all the possible slices with different sizes. So that's why you have 0 to 4 for y, and x is from y to 4. Okay, so this is not a constant anymore, so different from the previous example. Alright, so in terms of integration, it's also not very challenging. We first do the integration first, right? So still here, do the integration first, okay? So what is the integration? Integration of 2 over x will be 2x, but the value at 4 and y, okay? So it will be 2 times 4 minus 2 times y, okay? Now we have a function y over here, right? Okay, so this is 8. This will be 8 minus 2y. So integration of 8 minus 2y over y. So integration of 8 over y is of 8y. Integration of negative 2y over y is negative y squared. Okay. Then evaluate 4 and 0. Okay, which will be 8 times 4 minus 2 squared, 4 squared, which is this is 32 minus 16, which is 16. Okay. If you check the size of this triangle kind of cheese, so this is 4, right? This size 4, this is size 4, right? And the length is height is 2, so it's 4 times 4 times 2. Divide by 2 because you only have 5. If this top is the rectangle or the squared, right? But you divide by 2, you get a half. That's why it's 4 times 4 times 2 divided by 2. This is also 16, which matches we talk about over here. This is also 16. Okay, so I hope this gives you an idea about how we compute the double integration and how it's different from the single integration. The key ideas for the double integration to do is you write it into the inner integration and outer integration. For the inner integration, you basically want to make your whatever variable in your outer integration, make that variable to be a constant, and you figure out what is the lower bound, upper bound. So you might be the case that the lower bound or the upper bound, when you make it into slices, because you want to make this one to be constant, you make slices, you might need to determine lower bound, which may based on the actual different y values. Okay, then based on that, you do the integration of the inner integration using the standard single integration, and then you do the external integration. Also, first following the standard integration, then you can find the solution for the double integration. Okay, so that's it for the double integration.